Hi, everyone. Today we have Chen-Da as our speaker. He's going to talk about his work, Adaptive Security of Multiparty Protocols, Revisited. Let's welcome him.
Yeah, thanks for the introduction. So I'm going to talk about this work, Adaptive Security of Multiparty Protocols Revisited. Yeah, this is joint work with Martin Hirt and Willy Maurer. And this was recently accepted at TCC 2021. So the work is on security definitions. So maybe let me start by saying a few words about definitions. So we want to build secure distributed systems, right? We want to build systems that satisfy some security guarantees. And what might be special about this compared to perhaps other fields is that it is very hard to check whether a system is secure, right? And in particular, it is hard because we don't know what a potential adversary can do. But what we can do is to use provable security. We can introduce a model. We can also introduce a definition and then give a mathematical proof that our system satisfies the definition. Right? Of course, this is a very hard task to do because we are very we want many properties from these security definitions, right? If, for example, we want the security definition to be maybe simple to understand, simple to use. We want the definition to be consistent. Maybe we don't want a protocol to be proven secure and insecure at the same time, right? Maybe we want composition. If I have a protocol that generates a key securely, I want to use the key in a further application, maybe in an MPC protocol or in symmetric key encryption, I don't know, something. And also, as equally important, we want the definition to closely match the practical application that we have in mind. And this is what I mean by completeness and soundness. Like typically, when we introduce a definition, we have some practical application in mind. And we want this model to match the application as much as possible. In particular, we would wish that any protocol that is proven secure under our definition is also secure in practice or in the application that we have in mind. And also, any protocol that is secure in practice should also be provably, like we can prove it secure in our model, right? Of course, this is kind of very challenging. And in this work, we focus on the setting of so-called multi-party computation, right? And the idea here is that we have a set of parties, and they jointly want to securely compute a function, let's say. And the way we can think about it is kind of like parties have access to a computing device, which can be the mobile phone, the iPad, laptop, whatever, can give inputs and so on. These are these small objects that I have there. And these devices are connected via some communication network, which can typically be the internet. And these devices jointly execute a protocol with the goal of constructing an ideal computer or an ideal system, which is what we have at the right. And the point is that the ideal system is secure and trustworthy, even when some of the computing devices in the left can be hacked. Right? And in this work, we focus on multi-party computation with adaptive security, right? And in this setting with adaptive corruption, what we mean is that the choice of corruption can happen during the protocol execution. And not only that, it can happen based on any information that an adversary has gathered so far. This can be, for example, information that he learned from the network, or information that he learned from upon corrupting the computing device of a party and learning its internal state, for example. So maybe these two guys are corrupted, and then the adversary learns the internal states and decides to corrupt the third guy, for example. Okay, so the question is, what can we guarantee in this challenging setting, right? And very intuitively, if you think about this from scratch, then what you would expect is that the security guarantee that you obtain depends on the actual set of honest parties that we have. And typically, you'd expect that the more parties are corrupted, the less is guaranteed. And usually, as soon as we surpass a certain threshold or some bound, then all the guarantees are lost. This is kind of what one would expect. But maybe even before talking about definitions, let's look at a very simple example. So consider the case where there is some client on the left that inputs a secret S. And he wants to jointly distribute the secret among a set of servers, which is at the right? In a secure way, let's say. So there are many ways to do this. I'm gonna talk about one way, like one concrete way. So imagine that the client chooses a very small set of parties at the right, of size kappa, let's say. And now he splits the secret into kappa random summands, subject to the constraint that the summands add up to S. And now they give one piece to each server on the right. Maybe like one question would be, is this a good idea, right? So any ideas? Like, is this good or bad, right? And if you think about, now it depends on what the adversary can do, right? If the adversary is static, right, let's say, this means static means that the choice of corruption only happens, let's say, at the beginning of the protocol, and more importantly, it is independent of everything else, right? We cannot choose the set depending on anything, basically. Then one can show that this seems to be a good idea if the adversary is static, because when the client chooses this small set, which is a committee, let's say of size kappa, then it's very hard that the client exactly chooses the set of corrupted servers, right? And as long as there is one on a server, then the secret is secret. S is secret, right? And if we have, let's say, a large enough number of servers, then the probability that you actually hit the bad set is very small, right? So one can kind of argue that if the adversary is static, then this may be a good idea to distribute a secret. However, if the adversary is adaptive, this is a very bad idea to store a secret, right? Because when the client distributes these secrets, these shares, the adversary can look at who sends message to whom, right? And then can figure out that these are the kappa parties that will hold a secret. And now he can adaptively make the choice to corrupt this small set and corrupt everyone, right? And therefore, an adaptive adversary corrupting kappa parties can always learn the secret with probability 1. So it's kind of like, even though I didn't talk about definitions yet, right? We kind of expect that if we do something like this, no matter which definition I propose, if the definition is supposed to capture something against an adaptive adversary, then something like this shouldn't satisfy the definition, right? But yeah, I didn't talk about what adaptive security means, so maybe let's get into that. So what is the standard notion of adaptive security in MPC? So this is, yeah, this was introduced by Canetti a few decades ago, right? And there have been, there is a standalone definition, also a UC definition. And the idea is basically to show that the left system and the right system are the same, right? I'm gonna change a bit the notation here. So I'm gonna denote the kind of the local computing devices with round objects. like I1, I2, and these are kind of the objects that execute the protocol. And the network just with a square box. And at the right, the ideal system, which for simplicity, we can think about it as it simply computes a function. It gets an input at each of these interface, computes something and gives an output, right? So what the adaptive security definition says is the left system and the right are the same. But of course, it's not as simple as that because here the right system doesn't leak anything to the adversary, right? Whereas in the left system, maybe there are some messages that are leaked through the network, or definitely if the adversary, for example, corrupts some of the parties, then he learns some internal state. So how do we model this interaction with the adversary? So what we have in the standard definition is we actually don't have purely the ideal system. We also have a simulator, right? We have an additional system, which is usually called a simulator. And the role of the simulator is kind of to simulate anything that the adversary sees in the left. This is usually called the real world, right? Like if the adversary learns, for example, the internal states of parties 3 and 4, then the simulator has the task to also output this information. And more importantly, he has to do this based only on the data of the current corrupted parties, in this case, 3 and 4. More precisely, the simulator has to output whatever the adversary sees, while only having access to the inputs and outputs of parties 3 and 4. Yeah, so maybe a bit more concretely, just as an example, in the case of secure function evaluation, like when we have the task to evaluate a function, then we usually have these different stages, right? The first is like we have an input stage, like all the honest parties define what their inputs are. And at this point, the adversary can choose who he corrupts, right? Maybe he chooses to corrupt party 3. Simulator has to, of course, justify the internal state of party 3 having access to this wire. Maybe the same for party 4, right? It's adaptive, so this like happens many times, right? And of course, if something leaks via the network, then simulator also has to simulate this part. And at some point after the input phase, all the inputs are defined. And now this box MPC has the task to basically compute the function and gives an output to all the parties. And this usually also takes time, right? The adversary learns the output of corrupted parties, and based on that, he can also corrupt further parties. So for example, he can corrupt party 5, let's say. And what the definition says is anything that happens, like intuitively, what the definition is saying is that anything that happens in the left system, in the real world, I can reproduce in the ideal world. This is kind of what the standard definition for adaptive security is. And even though it's very intuitive, I would like to argue that it gives us some technical challenges, right? In some aspects, it seems to be apparently too strong. And one of the main examples is the so-called commitment problem. And I'm gonna explain what I mean by the commitment problem with a very simple example. So consider the setting with 2 parties, party 1 and 2, and they are connected via an authenticated channel. So let's say this is not confidential, it's just authentic. And now let's say that party 1 inputs something to the protocol, has a secret input x1, and he commits to this input using some commitment scheme, right? And because the channel is authenticated but not confidential, it means that the adversary learns the block, right? The commitment to the input x1, and therefore the definition says the simulator has to come up with a fake block B prime, right? And the point here is that the block B prime has to be generated without the knowledge of X1, because at this point, party 1 is honest. Right? Of course, the problem now is that if the adversary adaptively corrupts party 1, then the simulator learns the input, right? And the adversary here learns the internal state of party 1, and therefore also learns the way the commitment was created, the randomness and so on. So the simulator cannot open this block to X1, so he cannot explain it consistently. And the question here is this a problem, right? So I'm going to try to argue that it is. Maybe we can discuss whether it is actually a problem or not, but let me give you an example. So assume that we are given a very secure protocol, like someone very wise tells us, if you do these steps, this protocol is super secure, right? Adaptively secure. And then someone naive, right? Like me, let's say, let's say that I instead of executing this super secure protocol, I first do some random stuff in the beginning, and then I execute the super secure protocol. And what I do with the random stuff is what I said in the previous slide, right? I kind of publish a commitment to a secret value, to a secret input. And the problem now is that the overall protocol cannot be proven adaptively secure because of what I said before. This means that the fact that I published this commitment makes the protocol insecure. I cannot prove it adaptively secure anymore. And this holds no matter how secure the super secure protocol is. And what is interesting is that this also holds even if the commitment is perfectly hiding. So even if the block that I publish is statistically independent of the input, I cannot prove the overall protocol secure. So how do we solve this nowadays? So nowadays, the way we go is we say, okay, we cannot simulate. So what do we do? So there are two main options nowadays. We use secure erasures. Like if parties can securely erase data, then we can still simulate. Like if party 1 erases his internal state, then nothing is leaked to the adversary, right? So we don't have the commitment problem, at least here. Or option number 2, maybe we use non-committing primitives, right? Maybe we use non-committing encryption, or we can equivocate and so on, right? And these are two ways to make the protocol adaptively secure under the standard definition, but the problem is we incur an additional assumption, or we need to use heavier crypto primitives, which incur an important efficiency loss. But I guess at a higher level, the question is, can we propose an alternative definition for adaptive security that doesn't have this commitment problem, right? And this is the question we ask in the paper. Is there a natural definition for adaptive security that is not subject to this problem that I just explained now? And the answer is yes. So what is our definition? So our solution is basically, the idea in our solution is to specify a guarantee for each set of parties. And this is just a statement. And the idea is that the guarantee for a specific set holds as long as the set as long as the set is honest. And as an example, I give you this example where we have 3 parties. So we have all these sets in the beginning. And in the beginning of the protocol, we have very strong security guarantees. All these statements hold, right? And maybe at some point, P1 becomes corrupted. And therefore, we lose some of the security guarantees. In these statements, many of those statements will not hold. But all those statements that have P2, like all those statements corresponding to sets that are still honest, still hold, right? In this case, these 4 sets. And maybe P2 becomes corrupted now. And then we still have these 2 guarantees, and maybe everyone is corrupted and we still have these guarantees.
Quick
Yes.
question. So will a corrupted party be released later? So like if P1 is corrupted at, let's say, round 1, will it be back to honest in later rounds?
No, I consider this the case where parties that are corrupted just, let's say, remain corrupted. We could also think about what happens with how is it called? Like if yeah, I forgot the name. With these proactive adversaries, right? That kind of change corruptions, right? But no, let's just, for simplicity, let's just think that once a party becomes corrupted, then he is corrupted until the end, right?
Sure.
And of course, what is missing in this picture is that the adversary structure is not there. Like typically, like this is, I would say that this is what you get, but maybe at some point you surpass the number of allowed corruptions, and therefore, and in that sense, then all the guarantees are lost, right? But I don't depict it in the picture. And I hope you agree with me that this is kind of the most general template that you would expect when you talk about adaptive security. I didn't specify what guarantee of X is. This can be an arbitrary statement. I will give a concrete instantiation afterwards. But I hope you agree with me that this is kind of the most general template that one can think about in the setting of N parties with adaptive security. We have events that matter. And the events that matter in an MPC protocol are the corruption events. These are the events where things change, right? Like maybe P1 is corrupted, P2 is corrupted, and so on, and the security guarantees change at that point in time. If we don't have corruptions, then the guarantees don't change, right? Yes?
So this solution is still in the context of the commitment problem. Is it like I'm asking from the sense that in the commitment problem, it was kind of non-interactive, that once a party commits, the other party does not do anything. Whereas if I think, say, when P1 is corrupted and a step of the computation involved 2 parties, P1, P2, then how do we capture that?
No, so this is meant to be like a very general, forget about the commitment problem. We can ask, what can we guarantee in the setting of adaptive corruption? So I would say that a natural way to give guarantees is I give a guarantee for each set of parties. This is a security statement. I need to say what I mean by this, right? But the statement holds as long as the set is honest. And this seems to be a natural template, in my opinion, because kind of the more parties are corrupted, the less is guaranteed, right? And at some point, maybe we have too many corruptions, and actually we need to drop all the guarantees, which I didn't depict.
Yeah, also just the guarantee statement that you have, is it round dependent or is it always the same statement? Or?
The statement is the same, and the statements are fixed in the beginning. These are like fixed. This is a very good question. So the statements are fixed in the beginning. Maybe the statement could be there is a simulator that does this and that, whatever, right? We fix, like in this case, 8 statements, and the statements hold as long as the set is honest. This is what I'm saying. This is what we propose as a template to give security guarantees. And now what the statement is exactly, we can be a bit more flexible in that and decide what the statement is, right? But the template is like that. So what is the instantiation that we choose in the paper exactly? So what we say is, now I give like a specific meaning of what the statement could mean, right? And by the way, this template also captures the standard adaptive security definition. You can give the statement, for example, for the empty set. This is the existence of a simulator that consistently explains the execution of the protocol, right? And all the others are just empty or whatever you want, right? And this template also captures the standard definition. But in our paper, we say, we give another instantiation of this template. And what we say is the guarantee for a set X is basically anything that is leaked to the adversary does not depend on the inputs of X. So any data that is leaked to the adversary can be derived from the data of parties that are not in X, irrespective of whether they are corrupted or not. This is a guarantee for set X, and as long as the set X is honest, anything that the adversary could have provoked or anything that has been leaked to the adversary, I could have provoked if I had access to the data of parties not in X. And the question is why doesn't this why does this overcome the commitment problem? Right? So to see that, just fix a set X, like this one, for example. If a party in the set X gets corrupted, the guarantee is lost, right? Because the guarantee should hold as long as the set X is honest. This is kind of what the template says, right? As soon as party 2 is corrupted, the guarantee is dropped, and therefore, what this technically means is that we don't need to simulate the internal state of this party because we are not giving any guarantee. However, another question is what happens if someone not in X gets corrupted, right? Like party 3, for example. In this case, the commitment problem also doesn't arise because the simulator had access to the input of party 3 beforehand, and therefore he can consistently explain his state. Let me go back to the simple example. Like, this is just a sanity check. We would like that the simple example obviously does not satisfy the new definition, right? This is just kind of a sanity check. So if we take, for example, the set X that contains only the client, what the guarantee for this set X means is if this holds as long as the client is honest. And therefore, when the client distributes all the shares, the adversary can adaptively corrupt any subset of the servers. The guarantee still holds, right? And in particular, the same attack as the normal in the normal adaptive setting applies, right? The adversary can adaptively corrupt the committees, the committee of the server committee, right? And learn the secret. And the simulator cannot simulate the secret because the simulator has to output the secret basically without access to the input of the client because this is inside the set X. Questions here? Okay, so we said that like we did a sanity check, but what is the definition really say, right? It would be nice to kind of try to explain intuitively what we achieve with this definition. And what we achieve with this definition is basically we fix a time t. What we are saying is that anything that has happened up to time t, in particular, any information that the adversary learned up to time t, you can deduce from the data of corrupted parties at that specific point in time. And this holds for any point in time. For example, if we have t here, where no one is corrupted, then anything that has happened to the protocol, any data that has been leaked to the adversary, can be derived from the data of corrupted parties, which in the left case is no one, right? In the case of T is any data that is leaked to the adversary can be derived from the data of P1. And what is different from the standard definition is that the explanation that we give at different points in time doesn't need to be consistent. Like in the standard definition, we require a single simulator that simulates throughout the entire execution. And now we are giving an explanation for each point in time, but the explanations themselves don't need to be consistent. And this is exactly what allows us to overcome the commitment problem. Intuitively, like I first output an encryption of 0, I become corrupted, I cannot explain it. But I can explain everything up to the point I become corrupted, and I can also explain everything if I knew the input of the corrupted guy. Right? That's kind of the logic. Yeah. So how do we model this this definition? So for this in this paper we choose to formalize this new notion in a composable framework, and we choose a constructive cryptography framework. And there is a reason for that. So in constructive cryptography, basically we have resources and converters, right? Resources are the objects that we care about, like the network and the thing that we want to construct, right? These are like the functionalities in UC. And then there are the protocol engines, which we call them the converters. And the idea is very simple. So we attach the converters, the protocol engines to the resource, and we get another resource, right? This is kind of the idea. And what is crucial in constructive crypto is that we don't consider single resources, we consider sets of resources. And this allows us to talk very naturally about security guarantees. Like for example, I have a protocol that works as long as the network has a delay between 5 and 10 seconds. But I don't want to specify what the network is, right? I don't want to fully specify the functionality. As long as the network has a delay between 5 and 10 seconds, I'm fine, right? So these objects are actually sets of resources. Any resource that satisfies the guarantee is inside the set. So any network between 5 and 10 seconds would be a valid resource. And maybe the same for the right object, right? Maybe we want to construct an MPC system or something that gives you some like accuracy or time limits as well, right? It's not like a single object. Is a set of objects. We are happy with anything within the set S, let's say. And the statement basically says, if in my protocol I assume any resource in the specification R, what I get is some resource in specification S. This is just a subset relation, right? So in our and why is this interesting, right? Like in our setting, we are giving a guarantee for each set X, and this guarantee can be captured with a set of systems SX. So basically, the set of systems SX is the set of all systems that satisfy this guarantee for a set X, right? Formally, it would be something like that. We have a simulator that has access to the data of parties not in X. And this holds up to a certain event where any party in X gets corrupted. This is not. This is just a formalization. But what is nice, I think, is that we can of course have an intersection of specifications. We can have a single construction statement that captures all the guarantees at the same time, even though we kind of require like a guarantee for each set X. We can say the protocol attached to my favorite network satisfies all the guarantees at the same time, meaning it is in the intersection of all these specifications, right? And this is the main reason we chose this framework, because then we can benefit from composition guarantees, right? Like we can express everything within a single construction statement, and that's it. So what are some interesting lemmas that we proved in the paper? So we basically proposed this new notion, and what we proved in the paper is that the new notion is actually in between the standard notion of adaptive security and just static security, right? So first, if you have a protocol that is, let's say, secure under the standard definition, then it also satisfies our definition. The converse is not true because of the commitment problem that I told you about before. And as a consequence, many of the protocols that are believed to be secure in practice, but you cannot prove them secure, right? Because of this commitment problem, you can actually prove them secure under our notion. And this is the case for like famous protocols like CDN or CLOS. Actually, CLOS is, what I mean by CLOS is the one that was only proven statically secure.
Are there like workarounds for these protocols that say avoid the commitment problem somehow, or?
Yes, like for example, CLOS is also adaptively secure if you have non-committing encryption, right? But the version of CLOS where that was only proven statically secure with plain encryption also satisfies our new notion. This is what is different, right?
Like, are you like used in practice, or is it more of a something like stuff that's like deployed where you believe it's secure, you just cannot prove it's secure under like the current definition? Yeah,
I would say that in practice, like I don't know, I would say that in practice you don't aim for, or in my understanding, you don't aim for full adaptive security. Like usually, if you have static security, then it's kind of okay somehow. Like it shouldn't be like that because adaptive attacks are very realistic, I would say, right? But the problem is that you pay a high price, right? You have to use non-committing encryption or something like that, right? And the second part, any protocol. So our notion is strictly stronger than static security, right? So if the protocol satisfies our definition, then it is also statically secure. And perhaps very importantly, it seems that our notion gives kind of very strong security guarantees against an adaptive adversary. And I just gave you a small example, like the example with the committees, right? This is statically secure, but it doesn't satisfy our notion. And there are other examples in the paper. Yeah, so with this, I finish the talk. So I'm happy to discuss or take questions.
Yeah, if anyone has questions, also please feel free to type them in the chat or just unmute yourself.
It's
You answered my questions during the talk. Yeah, all of the questions.
Oh, I think we have one question.
What if you want to use a UC framework? Yeah, that's a very good question. So if you want to use the UC framework, right? Then you have different options, right? So who was asking this? Daniel, yeah, like such a long time. So if you want to use UC, I guess if you take the definition as it is, then I would say that it's not obvious how to capture all the statements within a single UC statement. And also it's not clear how you can compose this, right? Like each of these statements hold until the set becomes corrupted and so on. So it's, at least to me, it's not completely clear. It's kind of like a protocol realizes many functionalities at the same time. And now we want some sort of composition, right? So I would say that if you want to capture this definition as it is, then you would need to extend UC in some way. But I guess you can also maybe do it differently. You can let maybe you can let the distinguisher choose which set is X or something like that. It wouldn't be exactly the same definition, I would say, but you can maybe phrase as like a similar definition in UC, perhaps.
There's a second question.
So
Any concrete example of a protocol that is secure in this notion but not standard adaptive?
that is secure under this notion, but not standard. Yeah, but this is like anything that if you have the commitment problem, right? Yeah, so let me just go over this again. So let me check. So if you do something like this, or maybe even like this, right? This is the commitment problem. This is clearly not standard adaptive secure, right? Because if you do the random stuff, you cannot explain the block that you publish, right? But this doesn't like if you look at this thing within in the context of our definition, the new definition, then it could be like then it depends on what you do in the super secure protocol, right? But the fact that you publish this commitment doesn't make the protocol insecure. Yeah. So the reason is that if I and the reason is what I try to explain like afterwards, right? Like here. So if I corrupt someone in X, if I corrupt someone in X, I don't care. I don't need to. There is no commitment problem by definition, right? Because the guarantee is dropped. And if I corrupt someone not in X, I can solve the commitment problem because I gave an advantage to the simulator. So this is like the first part. I hope this was.
So sorry. So I hope you can hear me.
Yes.
Yeah. Okay. So in the commitment problem was that you corrupt a guy and then you can't later explain what's happening, right?
Correct. Yeah. Like the guy has an input. Of course, we need to specify what the commitment problem means, right? Like what I mean is exactly this. Like I have a secret input, I publish a commitment or an encryption. Later I become adaptively corrupted. I cannot explain the commitment, right? This is what I mean. There are other forms of commitment problem, right?
So in this specific example in the new notion, you're saying if this X1 guy is part of this set X, right? This guarantee X that you have, and you say that if this guy is corrupted, you just refuse to explain. That's it. I mean, you don't care. Correct. Is that what you're saying?
Yeah. Yes.
Okay. Got it.
And if the set is party 2, for example, then I have to explain it, obviously, right? But then I have access to X1 and then I can actually do it. Yeah.
Okay.
So, and what was the other?
The other question was about the sanity check that you went over. Yeah. Could you just go over it once again, please?
Yes, of course. Yeah. So it was this, I think.
Yeah, exactly. Yeah.
So we would like, obviously, when you propose this definition, you don't want this protocol to be secure, right? So if you pick X as the only containing the client, right? Then the guarantee holds as long as the client is honest, right? But the attack doesn't require the attack doesn't require to corrupt the client. So you can corrupt all the servers, and the simulator has to. So the adversary learns the internal state of all these servers. In particular, he learns all the summands, S1 up to Sk, subject to the fact that they add up to S, right? So the simulator has to output this without knowledge of S, because S is exactly the client, right? And
I
you
see.
cannot do that because, yeah.
Okay, so you just want to show that this still remains insecure in the new notion.
Yeah, this is just a sanity check, right?
Okay.
Kind of a notion that is supposed to capture adaptive security, then you don't want this protocol to satisfy the notion, right? Because intuitively this shouldn't be adaptively secure, right?
Got it. Thanks.
Okay, I think that's it. Oh, wait, yeah. Okay. Let's thank Chen-Da again.
Thank you.
And thanks everyone.